So it looks like we're going to get started. So I'm going to hand it over to our moderator to begin. You?
Hi, hello everybody. Thanks for joining this session. We have 5 sessions, sub-sessions today. The first speaker is Benjamin Gannon from Colorado State University. His talk is about fuel break effectiveness in Southern California. Ben?
Thanks, Wei. Again, I'm Ben Gannon. I'm a postdoc at Colorado State University. I'm going to be presenting on fuel break effectiveness in Southern California. And I want to acknowledge that this is part of a larger project that's funded by Joint Fire Science. It includes researchers from Colorado State University, U.S. Forest Service Rocky Mountain Research Station, and Oregon State University. So this Joint Fire Science funding call was really aimed at helping to solve the great fuel break debate and help us kind of hone in on where we fit within the space of whether fuel breaks are this efficient fuels reduction strategy to limit fire sizes and damages, or a rarely effective strategy for managing fires with negative aesthetic and environmental consequences. And so our larger project has the goal of building better probability of success models, evaluating the potential effectiveness of current and planned fuel break networks, and then also combining that understanding of effectiveness with risk assessment modeling to design optimal networks. And I'm really just going to focus on that first piece today. And I'm going to hone in on one of our study sites, which is Southern California. We're looking at just under 2 million hectares of national forest on 4 national forests in Southern California. The reason we're focusing here is there's been a lot of fuel break building, maintenance, and research in Southern California that we were building on. And so the slide photo that I have there on the right just gives you an example of what a lot of these fuel break networks look like, where they're oftentimes focused on major ridgelines with some peripheral fuel breaks leading off on minor ridgelines. And they can be located with roads, but not always. So to get into the methods, we're starting from a fuel break polyline data set that originated from USGS from Brennan and Keeley. And it was updated by some Forest Service staff in 2015 for part of a fuel break planning project. And we've done some pretty minimal efforts to clean this data set up so far, basically to standardize the geometry and attributes. And I'll mention a little bit on the next slide that that carries some limitations with the analysis that I'm presenting today. But in total, we're looking at just over 5,000 kilometers of fuel breaks. And you can see on the map on the right how those are distributed across the national forests, where the Angeles National Forest has the most and the Cleveland National Forest has the least. So to look at fuel break effectiveness, we're really looking at the final outcome of whether these fuel breaks held when they engaged with wildfires. And so we're looking at wildfires from 2 different periods today, 2010 to 2020, to look at just the outcome statistics. And then from 2017 to 2020, we've got more data that we're using in statistical analyses of fuel break effectiveness, trying to find out what those drivers are. And these were compiled from a variety of the standard national data sources. We ended up with 385 fires in total that interacted with the national forests over the time period of interest. And to try to understand what the potential fuel break effectiveness drivers are, we've really assembled a large data set potential predictor variables ranging from fire behavior. We're pulling from things like MODIS and VERS to get the fire behavior, like fire radiative power, daily growth, and spread direction. We're looking at some of the suppression data sets to get a sense of whether these were utilized on incidents as fire line, whether there was aerial support for some of these lines. We're looking at what that daily weather was so that we can understand what those drivers are of fuel break effectiveness at a daily time step. And we're also looking at some of the landscape characteristics, the fuels, the topography, and accessibility. So pretty standard stuff. So I mentioned I was going to point to some limitations. Currently, the data set that we're looking at right now, although we're calling it fuel breaks in this presentation, it's really a mix of pre-fire fuel breaks, so things that are managed from the National Forest Fuels Management Program, also with some semi-persistent dozer lines that are things that are created opportunistically when managing wildfires in the landscape and persist for a number of years. And then also some pre-attack lines, which may not actually have any fuels modification, but are places that the National Forests have identified as strategic control features. And so we're actually in the process right now of attributing these features with a width and condition rating that will help us better distinguish between these. But just know that right now we're looking at kind of widely varying features that could be hundreds of meters wide to something that might only be 5 to 20 meters wide and created by a dozer on an incident. So in terms of the methods, we're using pretty standard stuff. We're basically creating spatial intersections of these fuel break polylines with wildfires. And what we're doing to create our samples is we're actually sampling the center points of 30-meter pixels. And so we're creating many potential individual sample points along a fuel break network to understand how the characteristics around that small segment of the fuel break influenced its potential for holding when it encountered fire. We're assembling those predictor variables using either just raster-based extraction if it's a raster-based product, or potentially a neighborhood summary. And I want to point out that the weather variables are extracted using a model day of burning technique that Sean Parks developed. And so it's a raster-based method in which we're estimating the first day that a fire engaged with each pixel on a landscape from modus inverse points. So in terms of the analyses I want to present today, the first is just going to be a summary of outcomes, again, over that approximately decade-long period. And when we look at those individual sample points, we're looking at a total sample size of about 65,000 samples. And then I'm going to hone in on a smaller data set from that 2017 to 2020 period in which we have the suppression data, which is really important for this project, which is about half that total sample size. And we're going to look at some univariate logistic regression and machine learning models for variable selection, and then some examples of machine learning for inference and prediction, drawing heavily on the types of statistical modeling that we've been doing for potential control line analyses that Kit O'Connor developed at RMRS. And then if I have time, we'll see, I might present some examples of kind of a simplified, more multiple logistic regression framework that we think might be a little bit easier for managers to apply some of the modeling that we're taking away from this. So jumping right into the results, the map on the right is showing the distribution of those 385 fires along with those fuel breaks that were encountered in blue. And so fires over this approximately decade-long period burned about 390,000 hectares across the National Forest, which is about 20.3% of the total area. And we did have a small number of fires that did kind of reburn the same area during this decade-long period, but it's a pretty small area, so I'm just going to ignore that for now. In terms of fuel break encounters, I mentioned there was about a little bit over 5,000 kilometers of fuel breaks and 1,463 kilometers engaged during this period, which is about 29.1% of the total fuel break length. So those histograms right there show the proportion of area burned by National Forest and then the proportion of fuel breaks engaged by National Forest. And the takeaway here is that the Angeles had a lot of fire activity and approximately the same proportion of fuel breaks engaged as area burned. But if we look at kind of the Cleveland and the Los Padres, we had proportionally more of their fuel break network engaged than kind of just the average area burn. And so that might be reflective that those could be potentially more strategically located in those forests, or they just lucked out and got more engagement during this decade-long period. So jumping into kind of how effective these fuel breaks were, again, we're just looking at, of those that engaged, how much held. The overall success rate was just over 30%. And then when we look at it across forests, it ranged between 26 to 44% of those fuel breaks held. And I want to note that that's really similar to what Alexandra Seifert found in the 2011 paper. It's actually almost identical. And so this is, I would hope being engaged in this fire planning space that we would be moving in a direction of maybe improving, but it looks like potentially that increased fire activity and a lot of those very challenging fires might have negated any gains we had by information sharing and learning. In terms of success rate by fire, the mean success rate by fire is actually a little bit higher. If you look at how much held on the average incident, it was 77% almost. And this is really reflecting that these fuel breaks are generally very effective on smaller fires, but not necessarily the largest fires. So in terms of trying to whittle down to kind of having a reasonable model that we could play around with, we went through a process of variable selection consisting of looking at the composite importance rates from univariate logistic regression, random forest, and boosted regression kind of approach. So these two machine learning approaches where we can get a relative importance value, followed by screening to eliminate variables with illogical relationships that we really couldn't explain. And then we follow that up with sequential elimination of highly correlated variables, moving from high to low ranks, because we were examining a lot of variables that are the same except at different temporal or spatial scales. And so we would eliminate those that are duplicative. And I've got a long list at the bottom, but I don't want you to kind of hone in on all those. I want to just kind of focus on those ones that are highlighted in red. Those variables that are really consistent across all these three approaches are whether it was used as fire line on the incident, some measure of neighborhood fire radiated power from modus inverse, daily area burn, whether it included an aerial retardant drop, really simple weather indexes like relative humidity and accessibility, which is reflected by distance to the nearest fire station. And so this is showing a simplified approach where we're using just boosted regression. What we're modeling here is essentially the probability of fire line holding, reflecting the top 20 most important predictor variables that we honed in on that last slide. On the right there is the relative importance ranks that we get out of this. And I'm not going to go deeper into this beyond mentioning that basically those same 5 or 6 variables that I mentioned on the last slide are the top 5 or 6 most important variables still here today. And then I want to point out that some of the things that we do see that are cool based on these models is we see logical relationships popping out of these machine learning models where we have higher probability of control if we have fire line incident or we have an aerial drop. We see decreasing probability of fuel break holding as we move further away from fire stations, and we get increasingly higher fire radiative power, and we get higher wind speeds. And so these are really kind of honing in on things that we already know, but capturing those interactions among these potential predictor variables into a model that looks like it could be useful. So I'm going to skip this slide because I did not account for the beginning introduction from our organizing committee. So I'll try to catch us up a little bit. And I'll show you just kind of an example of a simplified model that might be easier for some managers to apply. And so this is using just a simple multiple logistic regression framework where we're looking at that probability or that outcome as whether it held as being a 1 or it failed being a 0. And taking the 5 most important predictors that we get from the screening process that we went through before, we can see that we get pretty simple and effective models using just the top 5 most important predictor variables, which are whether we have fire line on the incident, the total fire radiative power within a 1 kilometer radius of each sample point, the daily area burned, whether there was an aerial drop, and the relative humidity. And so we see that it looks like we've got some models that are coming out of this process that could be useful in management to help estimate the probability of success on a given day. Something I'll point out here, these are just showing the marginal effects of each variable, where our categorical variables, that's those suppression pieces, showing the difference between no suppression and then fire line and aerial drop in these lines. And so you can see that the effect of suppression is really high on here. But it is moderated by the environmental characteristics. So to have some time to answer a few questions, hopefully I'll try to be brief on this slide, but the takeaways that we're seeing so far is that there's a lot of alignment with the earlier Seifert et al. Work, showing that suppression greatly improves effectiveness. And if you want to see just what those average effects are, that contingency table that I have up on the right is showing the probability of fire line holding as a function of whether it was used as fire line in an incident, and then whether it was combined with a retardant drop. So we can see that those lines that didn't have any kind of suppression had very low probability of holding. And then pretty good odds of holding if we put some effort into those. And so we know that suppression is really important. Part of that relates to accessibility, so how close it is to a fire station. We confirmed the importance of weather, but with a lot more specificity than previous analyses, so we can start to hone in on some of the things that are better for prediction potentially than just fire size, which is what Seifert et al. Had used as an index of fire weather. So we can look at what those thresholds potentially in wind speed and humidity might be that affect probability of control. So far, something that we're not seeing in any of those model results that I presented before are really strong effects of vegetation, which from a perspective of understanding fuel break maintenance and design is not a great thing. I would point out that some of the partial dependence plots we get out of the boosted regression models do confirm that fuels management has an impact. We have higher probability of control if a fuel break is previously burned or maintained, has lower canopy cover and lower total biomass, but those weren't strong predictors in the model. And we're hoping we find a stronger signal when we have those variables like width and a maintenance condition that we're collecting from the nape imagery. We also had relatively limited influence of topography. And part of this might have to do with the fact that a lot of these fuel breaks are just located on ridgelines since we don't have a lot of diversity. And so to potentially answer questions about where we might want to put fuel breaks on the landscape could benefit from a modeling approach in which we actually look at observations that extend beyond the fuel break network to get at where are those places in the landscape that natively have higher probability of control that could be enhanced by adding a fuel break. So with that, I'll pause and take any questions if there are any.
Please feel free to ask questions if you have any. So Ben, I have a question. Just maybe get it started. Can you hear me? Okay.
Yes.
Do you see it seems like a fuel break is a natural extension of the road network. Do you see any fuel breaks that are not connected with any roads?
Yeah, we do have a lot of fuel breaks that are not on roads that were in this data set. And interestingly, we did include a variable as one of our potential predictors that was whether it was co-located with a road. And that did not end up being a very important predictor variable, despite that I thought it would be, given that having a hard fire break like a road seems like it would greatly improve the ability to stop a fire compared to just fuels reduction in the ridgeline.
Okay, thanks. Are there any other questions? You can ask directly or you can type into the chat. All right, I guess we can move to the next. Thanks, Ben. And we can probably move to the next presentation, which is mine. And is also pre-recorded. So I will just let Mary to start the video. Thanks for coming to this presentation. Here I'm going to introduce how to use machine learning models to study factors influencing the risk of a fire parameter impacting wild and urban interface. I first want to acknowledge my co-authors for their contribution in data modeling ideas and model review. This is not a new subject. Many past researchers have done analysis related with this field. Here is a list of 8 publications to provide a context. So in this study, I'm trying to analyze the joint impact between multiple factors influence the WUI fire impacting risk. Those factors could include the relative position between WUI and the fire parameters also the weather conditions, also the fire parameter, fire suppression effort. I also want to take advantage some of the available research result, including the composite landscape measurements of suppression difficulty index and potential control locations. Other contribution of this study is we want to create fire spread funnels to support focal analysis. We will see that example. So we selected 11 fires in this analysis. We want to select more, but collecting a complete site of fire information is not easy. There's often missing data for many of the fires. So those 11 fires are mostly located in the Western US in 2017 and 2018. Here is one example about the fire parameters, which represented by different colors of lines, and the fire lines represented by the brown dashed line on the right side of this map. We also included UV polygons represented by those light gray polygons. Here is other example, has a little bit more complicated fire lines, fire parameters, and UV. So we can see from these two examples, it is pretty difficult to be focused on each pair of fire line and UV. So in order to be more focused, we create these samples. So each sample include one fire line and one UV. We buffer the fire line. We also buffer the UV by the distance between them. Then this overlapped buffer create ellipse. This ellipse can be used to clip out those other spatial informations like SDI, PCL, loads. We also overlap this ellipse with the fire lines. So to be more focused even, we will create these fire impact funnels starting from the UV. These funnels will open to the fire parameters. And we will also measure the percentage or the ratio of this fire funnel edge that exposed to the fire parameter. That means if this funnel edge is exposed to the fire parameter, fire can spread through that exposed edge and reach to the UV without encountering any of these barriers created from the fire lines. So we feel this ratio is important, could be important, and we call this ratio as leak ratio. Here are a couple of other examples for the fire line, for fire parameter and UV sample. We extract the probability spread map, SDI map, the fire line data, the rows data, and we create the funnel. So on the right side of this graph, you will see two funnels, but both of them are broken. The reason they are broken is because of the fire lines. Fire lines serve as barrier. They break the funnel, which is a good thing because we know then the UV is protected from the fire parameter. We also included weather data. Here we listed 4 of them. for measurements of weather, the temperature, relative humidity, wind speed, and gust speed. You can also see there are high correlation between air temperature and the relative humidity, with a high correlation between wind speed and gust speed. That means we don't need to use all of those variables in the future to build a model. So we end up, by doing this spatial analysis, we ended with several dozens of potential explanatory variables. We don't want to use all of them. So we tested different model formats, and we finally, we think those 8 variables listed here potentially are useful. Those variables including rows, suppression, temperature, gust, vapor pressure deficit. So that those are the 8 explanatory variables we consider. And for the WUI and for each pair of fire parameter and WUI, sometimes the WUI will finally be impacted by the fire. Sometimes the WUI was not impacted by the fire. So we mapped those data by these 2 categories. And it's sometimes difficult to tell from just observing these histogram patterns. So we calculated a correlation map between those several explanatory variables. We can find there are some correlations, but those correlations may not be systematic. It could be just spontaneous correlations, like a road sum within the funnel and the max gust. They are correlated, but there's no clear logic there. We also created some scatter plots to study the detailed relationship between explanatory variables. For example, we found road density is positively correlated with land density within each funnel, which is not a surprise. We also found land density is negatively correlated with leak ratio within each funnel, which is also reasonable. So those are the preliminary studies, and to be more thorough, we also created a logistic regression model, and we started with many explanatory variables, and we ended with 5 of them in this logistic regression model. We can tell those 5 variables have a significant impact, and also their sign, negative or positive, are in the right direction. One problem of this logistic regression model is the test accuracy is only 72%. It's not very high, just because even by doing random prediction, we could get a test accuracy close to 50%. So we try to improve our prediction accuracy by building a random forest model. Hopefully this can help us capture some of these nonlinear relationships better. We use as typical study, we use testing data and training data. 75% of the samples are used for training, 25% used for testing. The classification accuracy is pretty high. It's higher. It's about 88% by average. And, but there is a variation between probably 80% and 93%. But generally, it's okay. It's not perfect. The confusion matrix shows there are some errors, but there are also pretty good accuracy of predicting both impacted or not impacted WUI. A little bit more interesting indicator are these importance of predictors. We found road sum within each funnel has the highest impact to whether the WUI on the narrower end of that funnel will be impacted by fire. And some other indicators like SDI, land density, max gust is also important. We didn't find the general wind speed has a big impact. I feel the reason is wind shifting is complicated. It's that dynamic. So capturing the impact from general wind speed is difficult. There may not be enough data for us to capture it, at least at this point. Partial dependence tells us logical stories. For example, if you increase the rows within a funnel, you should see a lower probability of that funnel that will be being influenced by the fire at the end. SDI, if you increase the SDI, you should see higher probability of WUI being impacted by a fire at the end. So those are reasonable. So general conclusion. So this is a study that I'm trying to figure out some meaningful management indications. And also I'm interested in figuring out whether focal analysis will be more useful under this context. It seems like a focal analysis will be very useful. Although our funnel are not perfect, we can keep improving it. And management implication will be like, okay, suppression line locations could be better organized to create contiguous barriers to protect a set of WUI. That may be ideal. That could be an opportunity of developing some optimization models to optimize those line locations. And I think those are the useful informations, but we potentially should continue to collect more data to improve our analysis. And that's the presentation, and any questions will be appreciated. Thanks. Okay, sorry about the quality of the video. Is some of the slides are not very good. If you have any questions, I will be happy to answer. Okay, let's start with next presentation. The presenter is Jesse Young from U.S. Forest Service. His presentation subject is statistics for manage fire for resource objectives. Jesse, you want to start?
Yeah, Wei. Thanks for that introduction. Yeah, everybody, my name is Jesse Young. I'm currently a postdoctoral research economist forester with the Rocky Mountain Research Station. And today I will be discussing changes in location and severity of wildfires managed for resource objectives following the 2009 wildfire management guidance. I completed this work with a number of other colleagues of mine from various management agencies and nonprofit groups. And Dr. Niguez and Dr. Evans took the lead on the work that I'm going to be presenting today. So as we're all aware, the climate has become increasingly arid, as depicted here in this correlation of a fuel aridity index with area burn. You can see here the blue represents time periods from 1984 to 1999, and then the red dots represent time period from 2000 to 2015. So it becomes quite obvious when you compare these two populations, there's a notable increase in area burned throughout the Western United States as the land becomes more arid. This increase in aridity is closely correlated with the area burned with high severity and the percent of high severity burned within an individual fire. And in turn, this has really led to this increased homogenization of the landscape following these large high severity patches that sometimes have trouble regenerating after the wildfire incidents. This increasing trend of wildfire activity has traditionally been addressed with fuels management operations that include mechanical thinning and prescribed fire that really work best when used in combination or as complements to each other when the goal is to reduce fire severity. But unfortunately, these traditional fuels management operations have failed to really meet the fuel reduction needs that we need, especially at an increased pace and scale that's really needed on the landscape to reduce these high severity fires. So another complementary tool is managing wildfire to meet resource objectives. And this has really been gaining popularity, especially in frequent fire ecosystems that traditionally experience a lot of low severity fires. For the purpose of this talk, I'll refer to these fires as managed fires, where these fires were managed with strategies of either monitor, confine and contain, or a point or zone protection for at least 50% of the fire's duration, kind of during that active burning period or before containment occurs. So a little bit about managed wildfires. We know that prior research has shown that managed fires are commonly used to meet resource objectives when weather and burning conditions allow. And this research has really started to pave the way for the development of tools used to guide the careful application of managed fire on the landscape. And for more information on this, Stephanie Mueller will be presenting this Friday to discuss some of these tools that are being developed. Research has also shown that managed fires are more commonly applied in the fall with some activity in the spring. Of course, during these shoulder seasons, weather conditions are more favorable to lowering the proportion of high severity fire. And then ultimately also increasing the patch complexity when high severity fire does occur. So these patches are better for habitat, and they're also more likely to regenerate as a mature forest as time goes on. However, there's still questions that remain about the spatial and temporal trends of managed wildfire in the recent past. And this is the topic of that I'm going to be discussing today. So our research objective was to examine a wildfire's distance to the wilderness area, also the distance to wildland-urban interface, wildfire severity, and the number of land management agencies that are used to manage these different wildfires. We examined these metrics across management strategy, where we compared wildfires managed with a full suppression strategy to wildfires that were managed to meet resource objectives or to meet resource benefits, these fires that we're referring to as managed fires. We then took a look at managed wildfire across regions, comparing California to the Southwest. And in this case, the Southwest is comprised of the US states of Arizona and New Mexico. And then finally, we compare managed wildfire within each region across the time periods, where we use the 2009 policy implementation to kind of divide our time period. So we end up with a period from 2002 to 2008 that we're comparing to a time period from 2009 to 2016. So just to walk through this process in a little bit more detail, we first examined the four aforementioned areas of interest by first comparing full suppression and managed wildfires. Then we focused on managed wildfires, and we compared the managed wildfires between regions. So comparing managed wildfires in California to managed wildfires in the Southwest. And then finally, we took a deeper look at managed wildfires within each region by comparing the fires across two different time periods. So as you can see here, in total, we identified the dominant management strategy for 1,434 wildfires. And as the tree depicts here, they have been kind of classified into each of their appropriate classifications for our analysis. When When comparing distance to wilderness and the distance to WUI, as well as fire severity, we used a cumulative distribution curve to first visualize the data. And then we tested for a significant difference in the population median, or the 50th percentile, using a quantile regression with a Hubert-White standard estimator to account for heteroscedasticity or non-equal variance in the data, primarily either between time periods or regions. And then when comparing the number of land management agencies, we visualize the data with a discrete distribution function, so essentially a couple of histograms. And then we compared the average number of management agencies using a mixed effect Poisson model with a Hubert-White sandwich estimator, again, using these techniques to kind of account for that regional variation and that temporal variation that's heteroscedastic over the population. All right, now for some results. So just as a quick reminder, we analyzed the cumulative distribution function at the 50th percentile to test for significant differences between these cumulative distribution curves. So essentially this 50th percentile is what is associated with these significance levels. In the first step, we're comparing full suppression wildfires depicted in black here, and then managed wildfires depicted in red. So for example, when we look at panel A, the average managed fire, which is represented in red, was significantly closer to the wilderness area, hence its line being to the left side here. And the difference between the two populations with respect to this upper echelon, you can see that it really starts to diverge as well. And then so conversely, when we look at panel B, you can see that full suppression fires were significantly closer to the wildland urban interface, with the black full suppression line to the left of the red managed fire line. And then in panel C, you can see that the medium managed fire had significantly lower portions of high severity than a full suppression fire, which is good news. And here we see that nearly 89% of managed wildfires have less than 20% high severity. And then when we compare this to full suppression fires, only 67% of full suppression fires have 20% high severity or less. So the managed wildfires are kind of meeting that objective of putting more low severity fire on the landscape. When looking at the average number of agencies involved during wildfire management, we found significantly fewer agencies are involved in managed fires when compared to their full suppression counterparts. So a full suppression fire commonly has 2 or more agencies involved, while managed fire is most commonly managed by just a single agency. So that's saying either just the Forest Service or just the Park Service without any kind of interconnection or interagreement with it burning across lands. In many cases, managed fires are usually managed with local resources, and there is some reluctance, as I was just referring to allow these wildfires to burn across boundaries. And then this has been discussed previously by Fillmore et al., who's another co-author on this paper. Now focusing on managed fires, we're going to compare California to the Southwest, with the Southwest again being the states of Arizona and New Mexico. In panel A, you can see that California managed fires are represented by the black line, and they are significantly closer to the wilderness area. And you can see that 73% of managed fires in California are actually within the wilderness. And this compares to only 17% of managed fires being in the wilderness within the Southwest, which is denoted by the y-axis intercept there in panel A. Panel B shows that the distance between managed wildfire and the WUI was not significantly different between the two regions. And then in panel C, it shows that the Southwest, which is represented by the red line, has significantly lower severity within their managed fires, with nearly 87% of managed wildfires having less than 10% high severity. And this is compared to only 36% of managed fires in California having less than 10% high severity. It is important to note, of course, that the California fires are still have lower high severity than many of the full suppression fires. When comparing regions in the context of the number of agencies involved with the average managed fire, the Southwest did show signs of having significantly fewer agencies managing these fires, but it really lacked any practical significance as the number of agencies really did vary very little. So for example, for every agency that was involved in a managed fire in the Southwest, there would be 1.08 agencies involved in California. So a very, very slight increase. And it's important to note, of course, that in both regions, most of these managed wildfires are still just being managed by a single agency. When focusing on the temporal differences in California, so kind of looking at California first, and then we'll move on to Arizona, we see that there was very little difference between the two time periods. One exception that I don't actually display here is that there was a dramatic difference in the number of wildfires. So while there was 42 managed wildfires identified prior to 2009, we could only identify 17 after 2009. So the number of wildfires that are managed for resource objectives really has kind of declined in this last time period. However, it's important to note again that most managed wildfires in California are within the wilderness area, both before and after. So that hasn't changed. And roughly 80% of managed wildfires have less than 20% high severity, as we see in panel C here. So many of these managed wildfires, while they may be decreasing in their number, they're still doing a good job getting some low severity fire out on the landscape. When comparing the number of agencies involved with California managed fires over time, we did observe, again, a significant decline, but again, there was very little practical significance, with the ratio being a nearly 1-to-1 ratio, both before and after 2009. So really not a lot of practical significance there, even though we do see kind of a little artifact in the data that's showing it being statistically significant. And then when focusing on temporal differences in the Southwest, again, there was very little difference between the two time periods. One exception, which again is not depicted here, is that the number of wildfires did increase quite substantially. There was 49 managed wildfires identified prior to 2009 in the Southwest, and this increased to 146 after 2009. So the number of managed wildfires had nearly tripled when you compare the two periods. However, it is important to note that 98% of managed wildfires within the Southwest are within 20 kilometers of the WUI, both before and after 2009. So they are doing a good job kind of getting some of that landscape around the WUI to have some fuels reduction treatments taking place. And then roughly 75% of managed wildfires in the Southwest included less than 5% high severity. So again, many of these wildfires are very low severity when they're being managed for resource objective. The number of agencies involved in the Southwest managed wildfire has also significantly declined. But again, as I've kind of been stating, I'm kind of a broken record here. There's very little practical significance. But perhaps more importantly here, we do see that from the time period from 2009 to 2016, there were a number of fires that were managed with 4 and 5 agencies. So we are starting to see a little bit more of that interagency decision-making process when allowing some wildfires to be managed for resource benefit over jurisdictional boundaries. So just to kind of summarize some of our findings, we found managed wildfires were closer to the wilderness areas. Many of them are in the wilderness. They're generally further away from the wildland urban interface on average. And we also found managed wildfires to be burning at lower severities and to be managed with fewer agencies. Kind of some implications as the practice of managed wildfire continues to develop and some more of these new decision support tools come online. It may be beneficial to reduce the distance between managed fire and the wilderness urban interface when burning conditions and weather conditions allow, of course, for the wildfire risk to still be effectively managed with a low probability of any negative outcomes. Our findings also confirm past research showing that managed fires do tend to have a lower severity and sometimes maybe a lower severity than is what is ideal. So with this in mind, it's important to note that with managed wildfires, to meet these objectives of fuels reduction, it may require multiple entries of these low severity fires, or it may require an increase in the severity to better kind of meet the pace and scale of the fuel reduction goals. Of course, not tipping over to being a high severity fire, but trying to just get some more of that kind of moderate and mixed severity in a work on the landscape. We also found managing fires to have fewer we found that managed fires have fewer management agencies. And this does kind of highlight this need to improve the interagency decision-making process so that we can start to manage more wildfires across different jurisdictional boundaries to get some more of those resource benefits on the landscape rather than to maybe be putting them out just because they're close to a neighboring jurisdiction. And then when we examined managed wildfires by region, we found that California managed fires were significantly closer to wilderness area, again, with 20 or 73% being within the wilderness. We also found California managed fires to burn at higher severities when compared to fires in the Southwest. But it's important to note that 80% of these California managed fires still contain less than 20% high severity. So they're still getting a lot of really good fire on the landscape and not a lot of large high severity patches out there. When thinking about reducing the distance between managed fires in California and the wildland urban interface, there may be a number of barriers that really need to be taken into account, of course. California has a very different ecology than the Southwest, a lot of chaparral systems that can be very explosive and hard to control fires under different weather conditions. There's also a recent ongoing drought in California. So this really could, of course, have a drag on using wildfires to meet resource objectives. And then ultimately, California does have a very complex wildland urban interface, which of course does complicate the application of getting more good fire on the ground. Managed fires in the Southwest were found to be further away from the wilderness and to burn at lower severity when compared to California managed fires. Again, 75% of managed fires in the Southwest contain less than 5% high severity. So many of these fires are incredibly low severity. One possible explanation for Southwest managed wildfires being further away from the wilderness area relative to California is perhaps the Southwest just contains less wilderness relative to non-wilderness areas. So that may be driving part of that effect that we're seeing there. And then as noted earlier, some of these very low severity wildfires may have a limited ability to meet resource objectives without multiple entries on the landscape or potentially increasing fire severity when burning and weather conditions allow for wildfire risk to remain manageable and still kind of get the desired outcome from the wildfire effects. And then finally, when comparing the temporal trends of managed fires within the two regions, the most notable result was really just the change in the number of incidents. So managed fires in California decreased over time from 42 wildfires from 2002 to 2008, just down to 17. So they were kind of on par with the Southwest prior to 2009. But then since then, they really started to diverge. Again, some likely barriers, as we discussed earlier, could include the local ecology of chaparral forests, also recent and current droughts, and the complex wildland urban interface. And then in the Southwest, we saw kind of the opposite, where the number of managed wildfires increased substantially from 2002, or from that earlier time period to that later time period, from 49 to 146 managed fires, so nearly tripling. And then, I think it's important to note here that the Southwest obviously is depicting a successful application of using wildfire to meet the resource objectives. And that while many of these fires may be very small and have very low severity, they really do increase the practice of applying managed wildfire on the landscape, giving some of those land managers the experience and the kind of local knowledge. And ultimately, we hope that it has the ability to build a strong foundation to allow larger managed wildfires on the landscape with a larger footprint and potentially with increased benefits beyond kind of what we're getting out of them right now. So with that, I'd love to take any questions that any of you may have, if we still have time.
Yeah, we probably have time for one question if anybody has other question.
It does look like there's one question coming from Huva that says, what data did you use to count agencies managing a fire?
We essentially used ownership. So if it burned onto their land, then we assume that they were involved. Of course, when some fires are really close to other agencies, they probably are aware of the fire, but we didn't count them as officially being an active management party until it had burned onto their land.
Okay, thanks, Jesse. So our next speaker is Dennis Yemshanov from Canadian Forest Service. He will do a presentation for the fuel treatment optimization. Dennis.
Hi, can you hear me?
Yes. Good. Yeah.
Okay. Wildfires cause significant economic damages and costly to prevent in complex terrain. Fuel treatments such as prescribed burns, strategic harvesting aim to reduce the risk of fire spread and cost of suppression. However, planning fuel treatments in complex terrain is challenging and requires a good understanding of fire behavior and careful planning. Optimization tools have been widely used to assist with fuel treatment planning, and typically a site-based fire risk or hazard metric is used to find the best locations of fuel treatments, and rarely we can see planning accounting for factors controlling directional spread of fires. But see works of UA, who pioneered the use of directional wind, basically directions in the planning of fire suppression activities. In this study, we address a knowledge gap and produce fuel treatment models, which is based on graph theory. We adapt a network optimization concept to assist with fuel treatment planning. A common fuel treatment strategy is to allocate treatments using a site-based priority metric. For example, risk of ignitions or fuel load or other metric. And we can start treating the sites with starting from highest risk of ignition, for example, until we all exhaust our project budget. However, this strategy doesn't reduce the risk of escaped fires, which can spread over long distances. To address this problem, we propose a network-based approach where we depict a landscape as a network of flammable fuels. Fire can spread between adjacent nodes in this network, and we conceptualize fuel treatment as reducing the connectivity between nodes to minimize the risk of fire spread through the network. Formally, we need to find key nodes in the network. Those removal maximally degrades the network connectivity. This is a critical node detection problem. In our simple network example on the left corner of the slide, we can see that a removal of one node greatly reduces a possible number of ways a fire could spread through the network, which is depicted by orange lines. And the model essentially allocates fuel treatments as preventive fire breaks. An important aspect of the critical node detection model is that it uses the network configuration, or we call it topology, to find critical nodes. Landscape networks are not that complex. They're essentially regular lattices, such as grid of connected patches. And it doesn't always give us full information about how fire may spread and how fire may behave in the landscape. So we need to incorporate the fire behavior expectations into the network configuration. The classical CND model checks for the presence of path connections from a given node to all other nodes. This is a like little graph on the upper left corner of the slide. In our fire spread context, we only need to check the path connections from a given node to other nodes where fires are likely to spread. So we don't need to check for all other nodes in the landscape because fires are unlikely to spread elsewhere. Everywhere. For each node, we find the other nodes where fires can spread using a fire simulation model. Fire simulation model generates probabilistic and spread perimeters of individual fires. And for each node, we select a set of fires which could spread from that node to other nodes, and only consider that set in the CND model, which is defined by this gray area in the graph on the lower left. The configuration of the set and the fire spread probabilities of fire spreading from that node are unique for each node. And this is the way how fire behavior information is incorporated into the CND model. This is a slide for those who really wants to see equations. The objective, I would suggest we just read the text in red. Objective function minimizes the expected number of pairs of locations in the landscape between which the fire spread is possible. And constraint essentially impose a treatment budget and checks for the presence of the path connections between all pairs of nodes where essentially fires could spread. You can find more details in our PLOS paper, and I will provide citations at the end of the talk. The definition of sites where fires ignited and could spread elsewhere is analogous to a fire sets concept, except we define the spread in an opposite direction. We define this subset as locations J, where fires ignited in, let's say, location I could spread to. And we can use fire spread probabilities between this location to rescale the decision variable that evaluates the path connections between this pair of locations in the CND model. And this gives us what we call a probabilistic fire shed scenario, which aims to reduce the spread risk of most frequent or usually small fires. The reason is why, because each decision variables checking for the path connections between a pair of locations is weighted by the fire spread probability between these locations. We could also convert the positive fire spread probability to binary 0-1 values, and we call it binary fire shed scenario. And it appears that this scenario aims to reduce the risk of spread of the largest fires, because it doesn't account for the fire probability information and only accounts for the potential spread area. So we have two distinct scenarios we could evaluate for the landscape. For practical reasons, we also need to control the spatial contiguity of fuel treatments, which the critical node detection model doesn't do. And the size of prescribed burns must be controlled for safety reasons, and the number of treatments, which can be limited by logistical constraints and weather, for example. What we did, we used a network flow problem to control the contiguity of individual treatments. Again, our paper provides full formulation, and I will only explain the basic principle. In a network flow model, which is a little graph on the left, we inject the flow into the landscape network from an auxiliary node 0, which is red arrows, and then we add constraints which require that all treated nodes must receive flow from another treated node or node 0. And this ensures that all treated nodes are selected as one contiguous cluster. We applied the model to the study area in Kootenay National Park, British Columbia, Canada. The park protects classical subalpine and alpine forests in Canadian Rockies. Fire management agencies balance historical fire regime and the protection of human infrastructure in the park area. We used a burn P3 fire simulation model to generate the patterns of potential fire spread in the Vermilion Valley under the current fire management regime. And this regime assumes that crews attack all detected fires in the park area, but approximately 13% of fires escape initial attack. Burn P3 is a well-known Canadian fire behavior simulation model that simulates the crown fire behavior according to Canadian fire behavior prediction system. and captured the spatial context of fire spread. The model uses large amounts of spatial data to define ignition probabilities, fuels, and fire weather on daily basis. And main burn P3 outputs provide the ignition locations and perimeters of individual simulated fires. And we calibrated the model to recreate the historical fire size distribution in the park area and used 30,000 replications of a burn year. We also needed to compose the landscape network for the network optimization model, and we did it from the maps of fuel types and terrain. We used a burn P3 model to calculate the probabilities of fire spread between all pairs of nodes in the fire spread network, which is this little dots, triangles in this map in the middle. And the problem is the map is too complex to read. The map of actual PJ values, it's essentially a green space. It is not easy to decipher where the fires are likely to spread from where. So what we did, we traced this probability to the nearest network edges, which is arcs connecting adjacent nodes, and using the shortest path algorithms. And the map of the right is easy to read, and it also shows predominant fire spread directions better. For your information, for your reference, the maps on the upper left corner show the burn and ignition probabilities for the area. The area has a large hotspots with a high risk of burn, and the slide shows the solutions without controlling the contiguity of prescribed burns. And in the left corner, lower left corner, the solutions show no fire behavior information, just the natural fire breaks only. And the maps show the solution for 3 budgets of 10, 20, and 30 treated nodes. Each node has approximately 1 square kilometers. So what model does, it cuts the central valley in half and isolates narrow valleys using single site treatments. The solutions on the right include the fire behavior information and show the binary and probabilistic fire shed scenario. Again, a binary fire shed scenario minimizes the risk of spread of large fires, and probabilistic fire shed scenario minimizes the risk of spread of most frequent fires. The model uses small area treatments to cut off the portions of the central valley and allocates the large treatments to fragment the hotspot with high burn risk. And probabilistic fire shed solutions mainly focus on fragmenting the hotspot with high burn risk. We also tested the solution minimizing the risk of ignitions only. This is the maps on in the lower left corner. The model allocated all treatments to sites with highest ignition risk and didn't fragment the area. On the right part of the slides, the maps show the solutions with the spatial contiguity control and fire behavior information. So we show 3 scenarios for 2, 4, and 6 prescribed burns, and the budgets of 10, 20, and 30 treated nodes. The prescribed burns aim to strategically fragment the area with high burn risk into smaller compartments. In this scenario, essentially works, the solutions show the model working as a fire break simulator. Okay. How we can compare the solutions? In these graphs, x-axis shows you the treatment budget, and y-axis on the left graph, y-axis shows the objective of minimizing the spread of large fires. And y-axis on the right graph shows you the objective of minimizing the spread of most frequent fires. And the lower values indicate the better outcomes. When the objective is to minimize the spread of large fires, which is the left graph, the strategy minimizing the risk of ignitions has the worst performance, and the binary fire shed information has the best performance, as expected. The scenario ignoring fire behavior information performed surprisingly quite well. but still not as good as a binary scenario. And the reason is because we have a complex landscape with pretty significant fire breaks, like rocky terrain and water bodies. So they already shape the potential spread of the fires across the area. When the objective is to minimize the spread risk of most frequent fires, the scenario with no fire information, which is based only on natural breaks, fire breaks in the landscape, had the worst performance. And the minimum ignition scenario had the second worst performance. This means that if you want to minimize the spread risk of frequent fires, you really need to know about fire behavior in the landscape, and you need to know fire behavior information. Overall, our approach addresses the shortcomings of fuel treatment planning methods based on site priority metrics and help account for factors controlling directional spread of fires. The use of the outputs from fire behavior simulation models help account for multiple factors controlling the directional fire spread and other factors which may contribute to the ignitions and spread of fires in complex landscapes. The model can be adapted to multi-period planning of fuel treatments and reducing risk of fires to human infrastructure, for example, industrial or recreational or human installations in forest landscapes. The model can also be used to compare alternative fuel treatment methods, such as prescribed burn versus strategic forest harvesting or thinning, and different treatments regimes, for example, using ground crews versus helicopters. And finally, our approach can be adapted to plan prescribed burns for protecting important ecosystem services, such as water supply, minimizing soil erosions, and protecting wildlife habitat. The study and details about this work are now available in our +1 paper. The paper is published already, and it's open access article. Feel free to download. Thank you. And I'll be happy to answer questions if I have time.
Thanks, Dennis. Are there any questions for Dennis? Yeah, now I figure out there is a question. Okay, Dennis, there is a question. In your analysis, how do you account for fire management that occurs on fires where there is also suppression, which means how do you account for suppression?
Okay, so the model, what model does, it basically anything, any suppressions or management activities, they are reflected in the fuel layer and input data which go into the fire behavior simulation model. So whatever activity we have which already change in fuels, we can feed into fire simulation model, and it will reflect and change the behavior of fires. So these probabilities of fire spread we load into optimization model, they already somehow account for them. The optimization model itself doesn't account for partial suppression because the critical node detection model assumes finding the nodes which reduce the connectivity. But we have a model modifications which allows partial reduction of connectivity, and that's the next model version we are currently working on. I see another question. What is the node size hexagon into your presentation, and how many nodes can you process on a standard PC workstation? It's a good question because critical node detection model is NP hard and NP complete problem, and who knows what it is? It means it's really hard to solve. We managed to process right now 1,500 nodes, and nodes doesn't need to be on the same size. So what we do, we create a hexagon network, a hierarchical hexagon networks, which we can aggregate for some nodes where we don't have really accurate fire behavior information, or this fire behavior information is not relevant. For example, locations very far from critical infrastructure where basically it's not that relevant to how we can protect this infrastructure, and the fire just comes from very far. So right now we're working on improving there are a number of tricks we can use, but right now we are about 1,500 to 2,000 elements in the network where we can solve full-size critical node detection problem.
Yeah, I suppose you can also switch to polygons without like irregular shaped polygons, right? You don't have to use this regular shape. Yeah.
Yeah, we can do a regular shape. In fact, the model doesn't see the actual shape of the polygons. The optimization model, what optimization model sees is a network. So whatever network we come up with, the model will digest, and it's up to analyst or up to a researcher to come up with an effective network, which essentially compresses the potential fire behavior in the landscape into as few as possible nodes.
Okay, thanks, Dennis. Okay, I guess we run out of time for your presentation. We will go to the next one. So the next presenter is John Hogland. He's from U.S. Forest Service. He's a research forester. His talk is about recent technologies in creating fire resilient landscape. John.
Okay. Thank you. Can everybody hear me okay?
You're good.
Okay. So to open up with here, we're going to talk about some planning techniques, new approaches to planning. And while in concept, it's not all that different. In practice, it is different in terms of the modeling approach here. And to give a little background here, a little outline to the talk, I want to really step into concepts of data science, decision science, big data, and I want to give a little background behind that, and then quickly jump into a use case scenario, and then talk a little bit about new coding libraries we're developing to facilitate these types of analyses and some improvements to the very specific use case that I'm going to describe here. So a little bit of a background. In this day and age, we have so much data that's available to us. How do we utilize this data to really start impacting our decision space with regards to forest management, wildfire management? And how can we best accomplish this with these various different data streams? There's a number of examples, but bringing it to the practitioner, bringing it to a use case that's actually practical in size and operation is still lacking. And so this talk's going to talk a little bit about that obstacle and how we're trying to overcome that, and then give that use case behind it to demonstrate that. And to help facilitate that, we've already built a whole suite of tools that deal with delayed processing and new concepts that utilize ArcGIS and spatial modeling. And this is related to a whole series of libraries, in addition to a large number of tutorials and tools and a series of courses and workshops and publications. However, it really is useful to see how this works in practice. So we're going to talk about a use case in Central Oregon, about 1.5 million hectares, Malheur National Forest, where we were trying to identify landscapes where we could reduce the severity of fire, reduce risk using some silvicultural measurements. And basically, in a nutshell, what we are going to do is use remotely sensed data such as Sentinel imagery and elevation models, do a whole bunch of transformations, mathematical machine learning transformations, to get outputs that define not only where we're going to implement treatments at very fine spatial resolutions every 30 meters on the ground, but also the costs of those implementations and potential revenues of that implementation, given all the desired future conditions to reduce fire risk and severity. And what we're actually doing here is just a whole series of spatial analytics, spatial modeling, but we're implementing all sorts of statistical and machine learning technologies that display this spatially, takes the geometry, the locations at the first order of importance here in terms of the prediction space. And we're able to facilitate this analysis quite quickly using these existing tools for that 1.5 million hectare area. But to really dive into what we're doing, it's easiest to think about it in terms of 5 different parts, where we're first quantifying current conditions using remotely sensed imagery and field data. And then we're defining desired future conditions in this context to reduce the severity of fire and reduce risk to WUI areas and resources on that landscape. And using that current condition, defining it in both fuels context for fire and also in silvicultural treatment context or management plan contracts, basal areas, trees per acre, we can then get at how much is being removed, so we can compare it to how much it would cost to move that material off the landscape and build it into a larger planning architecture. We can get at costs and revenues associated with the different types of treatments across that landscape. And one of the things that's quite unique in this context is the spatial scale and also the accuracy. In this context, we're not really looking at trying to come up with the best model for a very small subset of the predictor area. Instead, we're looking to come up with a model that is good across the entire predictor variable space. And so to do that, we actually have to address concepts of design. We want spread and balance. And so this has led to a spread and balance publication in which we have demonstrated techniques that do spread sample design, take existing samples and spread it out across the predictor variables space, and how that improves the accuracy. And more generally, what we're talking about here is getting a representative model for the entire landscape and how that improves on that accuracy. In addition, in doing those simulations, we also found the importance of empirically based standard errors. And I'm going to jump into that in just a second here. So we took this modeling concept, this design concept, and we built a series of models that define not only the land cover types in very generic sense, pine, fir, non-forest for that entire landscape at that 30-meter resolution, but also metrics that we use in forestry to define forest health, which correlate strongly with fuel compositions. So we got it basal area per hectare, trees per hectare, saw log above ground biomass, and also the total above ground biomass. And what we can see here is that we have very accurate models in terms of overall accuracy for these class categories, but we also have highly correlated models, not just for portions of the predictor variable space, but the entire predictor variable space. And so we can now use these as raster surfaces to across the entire gambit at every 30-meter. We can define something like our most likely class to say whether we're dealing with primarily a fir or pine dominated forest type or non-forest area. And we can also get at the probabilities themselves. We don't necessarily need to just do a hard classification. We can look at those individual probabilities for those cover types. Moreover, we can look at the error estimate of those cover types. In this context, we're using that GAM, generalized additive modeling approach, and we're using an ensemble of them. So we're empirically deriving what that standard error is for each one of our surfaces. Likewise, we can do this for basal areas per hectare, trees per hectare, saw log biomass per hectare, and tons of above ground biomass. So we can get real accurate depictions at very fine spatial scales across the entire extent of our study using these types of tools and these types of modeling approaches. We can incorporate standard error into this estimate too, because we have empirically derived standard errors that we can then use in our decision-making space. So now that we have this, we have the overall existing condition, we can take those existing conditions and compare it to our desired future conditions. And in this case, we can really define what we want on that landscape as it relates to wildfire severity and risk. And so what we can really look at here is we can define rules. And these are fairly generic rules that we put together for this use case, where we're not actually going to be doing anything where there's slopes greater than 50% or within streamside management zones. But when we're on a potential operational delineation unit, which is defined by a wide range of fire risk severity and human expert opinion defining where those boundaries should go. And we'll look at some of these spatially depicted across this landscape. We can then begin to set different thresholds. We can say we don't want fire to move across a given pod area. We're going to use pods as a potential management tool for mitigating fire and reducing risk. And so we don't want it moving across those pod boundaries. We want to contain it within pod boundaries. And we can set existing basal areas to something like 15 square meters per hectare. Likewise, within the pod boundaries, we can then look at it with a little bit more of a relaxed assumption. And we can look at north aspects because they can contain more trees and reduce the fire spread. When there's 27 square meters per hectare, or on south aspects, 20 square meters per hectare. But we can build those rules into play, and we can spatially define them, and we can subtract them from the current existing condition to get at what removals and where they're located. And then furthermore, we can take those removals and convert it into something that represents a market for use, in this case, tons of removed saw log or overall biomass. Likewise, we can define how much it would cost to move that material across the landscape using least cost path algorithms and looking at what the cost it would be to move along a road network and moving material from the land to the closest node along the road network, on that road network. And really what we're doing here is converting surface distance into travel times and implementing a series of overlays based off a series of rules that take machine rates and convert those dollars per hour into a dollar per ton, which we can then map back to overall removals to get at what is the anticipated cost for implementation. What's the expected revenue represented in this middle diagram here? And what are potential profits to meet our desired future conditions? One of the things I'm kind of highlighting here is that this is a very spatial question. And this is and it becomes very simple when you organize your question in this context. And so what we can easily incorporate are things like gate prices, and we can dynamically calculate those using this delayed reading concept. And for the tools we've actually built in our own coding language that allows us to script this up and use it very quickly. But we can then zoom in and actually look at what are the profits, what are the potential profits, where is it negative, where is it costly to implement prescriptions to reduce wildfire risk, and where is it profitable to implement those prescriptions. And then we can then look further at this within that pods concept. And within the pods, we can summarize all these departures from our desired future condition and get at how many tons are being removed and how many acres. And one of the things we can easily see is that because we're reducing the overall the number of tons on the landscape to mitigate spread across pods, we see that there's more material coming off the landscape along those pod boundaries than there are within the interior of those pod boundaries. However, there's less area being treated. Now, when we look at it in this context, what we really notice is that there's a lot of areas with low amount of removals coming off that landscape in terms of tonnage. And we're going to go ahead and zoom into two different pods that represent a restore objective. And as we can see, there's quite a range of values here. Moreover, we also know that there's issues with error in our models. So we can incorporate all that into our decision space and get at something that's really more like an operational treatment unit that really represents reality as opposed to an ideal. And in this case, we put something together where we looked at contiguous regions with more than 3 tons per hectare at a 95% confidence interval that amount to greater than 5 acres in hectare, or 5 hectares in size. So now we can really see these green areas really represent what are operational units to meet our objectives across that landscape. And we can zoom in and see how that impacts pod A and pod B. One of the things that we see when we do that is we actually change our summaries. We see that there's much less that's actually going to be manipulate on that landscape than if we were to summarize it at that total amount. And we can actually get at some questions that relate to whether pod A, which represents a scenario where we're going to try to maintain resources inside because of its proximity next to WUI areas and protection zones, versus pod B, where we're trying to mitigate spread into that protection zone. We can see how those trade-offs in terms of what we're meeting our objectives and how much they might cost and how we can plan out in the future for this. So with that being said, we now have a set of tools where we can look at 1.5 million hectares fairly easily and quickly within a couple hours. However, what if we want to look at all the West Coast? Or what if we want to look at the continental US or all of Canada? We're moving these tools into the next phase of development. In fact, we're migrating some of the concepts and ideas that we built within our Armorous raster utilities into a DAS-based processing system in which we can utilize Python coding directly and optimize C routines and really get at some parallelization and delayed reading improvements. And the basic idea here is that we're going to make this very flexible. We're going to make it so that it can work off desktops or server environments so that we can actually take advantage of high performance computing and cloud type processing. We're going to standardize our code so that we're working within common data science background and processing. And we're going to really focus in on automating scheduling and memory management so that we don't have to worry about that when we're actually processing these data. And we can, in this case, utilize our hardware and software to its fullest. And the way that we're actually doing this is using things like data frames, arrays, and bags, and we're parallelizing the data. However, we're not limited to parallelizing the data. We can also parallelize the process. And so we're building these libraries to do that and facilitate that processing. So what does that mean for this analysis per se? Well, there's a couple areas where we can really improve our estimates. In the example I gave, we had some basic machine rates corresponding to skidder type systems. Well, those don't always hold steady across the entire study area. They may change based off topography. They may change based off a system. So we can define that spatially. So we've got projects in play where we're going to actually utilize some existing empirical data with remotely sensed data to begin estimating those types of surfaces. And here we can kind of get the general idea. We're going to use those examples of projects where we've actually calculated costs and costs of implementation, and we're going to relate that to remotely sensed data to come up with spatially explicit rate surfaces, which we can then build directly back into our processing libraries. And with that, I'd like to open up to any questions.
Yeah, great. Thanks, John. Are there any questions? So I have a quick question, John. So you have a desired condition and you have a current condition, and there certainly is a gap. Are there any mechanism to fill the gap in your system? Like how do you move the current to the desired? Is there a planning or?
Yes, that's part of the process, and it basically is the desired future condition is defined within the context of desired basal areas or tonnage or cubic feet or however you want to look at it. And the existing condition is defined in that same way. And so then you do on a pixel by pixel raster math to subtract the two of them to get at what is the existing or what is the removal off that landscape. And then you can begin to define where you actually implement those procedures.
Okay, where probably also when, right?
Yep.
Okay, great.
Likewise, you can integrate growth and yield into this because each one of these cells can be grown.
Yeah. Okay.